Thank you for this introduction, and I'm really honored to be here. Actually, this university is my alma mater. I'm in the optics department. I think I'm honored. This is a pleasure for me, and thank you for the organizer for asking to inviting me. So my lecture today is mostly like a popular lecture. So I have divided all the mathematics and the research, mathematical work that we have done. I'm just going to present some of the results that we had and in which fields we are actually working on. So before going into that, I will just spend a few times of what is the importance of this day. So as we all know that in May, 16th May 1960, there is the first successful demonstration of the laser source by Mayman. And in today's world, as we know that since we are facing a lot of problems like climate change and energy requirements, so we need a lesser amount of energy to do our work. So our objective is to find out whether light can be a good agent for these purposes, right? So this will be my lecture plan. So I'm sticking into this that first I will spend a few times of discussing some of the emerging technologies where optics is playing a crucial role and what the state of the art in these fields. And then I'll discuss some of the things that we do in IIST. And we are actually started this research work from 2020, right? So we are also learning things. So I'm going to share the result that we have able to learn in this, and then maybe there's a lot of things we have to learn. So I'll discuss some of the scopes and opportunities there, and of course, if my lecture is interesting enough, so I'll expect some of the feedback from your side. So before going into that, let us briefly discuss what are the advantages of optical technologies. So it offers a high bandwidth, as you all know it, that if we want to do a large amount of data transmission from one point to the other end. So we require a carrier frequency which will be much higher, and light can produce this kind of high bandwidth. It has a low loss over distance, and especially for the guided wave. Like nowadays, the optical fiber that we use for the standard telecommunication, it has 0.02 dB loss per kilometer. So it's a very low loss devices. They are immune to the electromagnetic interferences, as Sarah was saying earlier. That nowadays we are almost surrounded with many devices which are using a lot of signals. So we require some kind of energy which is non-interacting with them. And since photon is less interactive to this, so light is immune to this electromagnetic interference. We have energy security, but of course this is for some perspective, not in general, right? And the antennas or the receivers of the devices that we require for the optics, because the frequency is very high. So we require the device footprint is very small, and therefore we can have some lightweight devices and which are compact also. Then power consumption is also very low. So these devices are not always very power hungry. So because of the high frequency and after the advent of the laser, we can have very high precision operation with these light sources, and it has a very wide spectral range to do it. Now it's another brief slides at how optics has shaped the 20th century. So with the advent of phase contrast microscopy in 1930, we know that it changes our outlook towards the microscopic world, right? Then comes the Hubble telescope and all other, which changes our vision towards the world, to the macroscopic world. Then on 1960, we have the laser sources, and that actually changed the entire dimension of the technology. Nowadays, we have these handheld devices. This cannot be fabricated without laser being invented or having an optics behind it. So you cannot have this high precision photolithography with these things. Then it also changes communication after the advent of optical fiber. We have a very high fidelity communication using optical fibers. Then it also changes in the entertainment world and the daily life. And now optics is still playing a role of changing the 21st century also. So now a buzzword is quantum computing, right? So these are new age computing, and photonics or optical beams or optical light sources, they are one of the main agents behind this. And they can serve a good purpose into this new age computing. There is also what is called a photonic computing, which is not exactly the quantum, but say parallel processing using photons, so we can do some kind of matrix operations using a very low-cost devices, compact devices. 5G and 6G communication, it is light is playing a crucial role for that. Remote sensing, it has been changed a lot these days, especially with the advent of LiDAR. Then quantum technologies, quantum devices, healthcare, biomedical sensors using photonics, they is actually changed the landscape of the biomedical devices that we have nowadays, especially during the COVID, right? Almost in every household we have the oximeter, pulse oximeter, and that's actually photonic devices, right? And the solar cell and the green energy. So these are the few areas, the emerging technologies where optics is playing its role, and I've just tried to tabulate it. There are many more applications are there. I'm just sticking to some of the points which are of our interest. And out of this, I'm going to talk about few of the fields where we in IIST we are working on. So in IIST, our field of interest is free space optical communication, mostly for the backhaul establishment. Then we are also working on hybrid RF photonic sensors, biosensors, because in some applications we have seen that though light signal, they have very precise measurement capabilities and they have very beautiful, strong candidate. But the penetration depth of the optical signal is very small. It cannot penetrate within few millimeters after our skin. On the other hand, there are RF signals. There are body safe RF signals, mostly around 2.3 gigahertz, which can penetrate better into the human body. So we try to think of a device where we can collect the data from inside the body using an RF signal, and then we analyze the RF signal using a photonic device. Why is that? I'll come into it later, because there are some problems for using the complete RF spectrum, right? So we need photonics to analyze these signals. Then recently we have also started our research on quantum optics, and we have two different axes of it. One is the quantum key distribution through free space links. So these are hand-to-hand with the free space optical communications. And we are also started working with photonic quantum devices. Mostly, it's right now it's a very new research. We started just 1 year, not in 1 year, 6 months back. So we have tried to figure out some what is called a quantum heat engine. So we are trying to find out whether we can have a integrated photonic devices where we can employ the properties of a heat engine, a classical thermodynamic heat engine, but a qubit will be there. So we have started doing this. These are mostly theoretical, but right now we are trying to establish the lab for it. So if we look into the backhaul network of modern day communication, so you'll see that we have the optical line terminals where the mask signals will come in, and then we have this to the local node or remote node, and from there it goes to the final user, right? And nowadays most of these are physical network. That means we lay optical fiber to do this one. But then there is some problem that you cannot lay down optical fiber at every point of it. There are some locations, some terrains where you cannot lie down the optical fiber. There are some applications where you cannot do the backhaul using an optical fiber. Suppose you are trying to, as Sarah was explaining in his slides, that if you try to communicate to an airplane or to a ship, so you cannot put a optical fiber to the end, right? So there we must have some kind of wireless backhauling, and we are trying to explore that whether optical backhauling can be a candidate of that. So to state of the art, recently, few months ago, there was a news actually that NASA Deep Space Communication, they actually received the image sent by a distant satellite, right, which is almost 40 times farther than our moon, and through our ground station. So this image has been encoded to a light signal, and then light signal traveled. So it traveled from the ground station to the satellite and then came back. And this was one of the major success that we had till date for the deep space communication. And this has done through the optical communications. Then there is this group from Nanjing University. They have shown that for 1 kilometer of distance, they have established a free space optical link, which is able to give a 9.16 gigabytes per second data over a distance of 1 kilometer. So these are where the modern day technology is there, and it is evolving till date. But our interest, so before going into that, let me explain a little bit like what is the problem of these outdoor FSO links. So whenever a laser light is trying to travel through the atmosphere, what we have is that our atmosphere is not a static atmosphere, right? We have a temperature variation. And because of this temperature variation, what happens that thermal cells build up. That there are some pockets where we have rarer air, right? So it's a low density, and in some places we have high density. Now we can think of two different length scales, right? So if the pocket of the air having a different density than the average density of the air, right? It can either act as a lens or it can act as a scatter. So if the diameter of this cell is of the order of a few meters, since we are using a light of, say, suppose 15 nanometer, so the cell diameter is very large and therefore it will act as a lens. On the other hand, if we have the cells which has a dimension of few millimeters, then they will act as a scatter. Now what will happen that when a light travels, right, and if you have a lens, then the lens will try to paint the light, right? On the other hand, if you have a scatterer, so when light travels through it, light will try to scatter, right? It creates speckles. So when the light travels through the atmosphere, we have both these small scale and large scale eddies are there. And as a result, we have, so this is just a representative image. So this is a Gaussian image that we have taken as input in our simulations, and this is the received beam at a distance of 10 kilometers, right? So you can see that because of the lensing effects, the beam tries to shift. So that is what is called a beam wandering. So beam will no longer be on the axis, it will try to move away. And for the small scale eddies, the beam will try to scatter also. So we need to mitigate these effects. Now the conventional technology is that we send this beam through the atmosphere, and on the receiver side, we have what is called an adaptive optics technology, right? So we have some kind of devices which can sense the instantaneous wavefront of the light which is coming to the receiver, right? Then the process is very simple. Once we determine what is the shape of the wavefront, we have a deformable mirror given as DM, right? So the deformable mirror will take the exactly conjugate shape of the wavefront. And when the light, the distorted wavefront reflects back, it will autocorrect itself because the light is coming from a distant source. So in general, it should be a plane wave. So once it is deflected from the mirror, so it becomes a plane. So we have the correction. And this is aggressively being used in all our ground telescopes, right? So nowadays, from the ground telescope, you can also have the image which is close to the quality of the Hubble telescope. That is because of this adaptive optics technology. But then there is a problem that this technology is very good for capturing an image. But whenever you are trying to do a communication with it, there lies the problem, because this setup, it takes some time because you need to sense the wavefront. You need to send the control signal to the deformable mirrors, and then the mirror will align itself, and then you get the corrected. So there is a latency. So there is a delay, and you cannot allow this delay to your communication system because this will add up, and you cannot tackle it if the data rate is very high. So instead of using Gaussian beam, right? So we can also have a new kind of structured light, which is called the light carrying orbital angular momentum. So what is an orbital angular momentum? So give you a hand waving idea. Normally, when a Gaussian wave is propagating, the pointing vector is parallel to the direction of propagation. Right? Now we can have the electric field can be polarized in any direction. That is the classic polarization. Don't confuse this with the classic polarization. Here, what happens is that the pointing vector is itself rotating about the axis of the propagation. So either it's rotating clockwise or it's rotating counterclockwise. So this is not the polarization, but the rotation of the pointing vector. And that's why the photon in this light will generate an angular momentum. So that's why this light is called orbital angular momentum carrying light. And the beauty of this thing is that we can have plus L orders and minus L orders. And all these L orders, they are actually orthogonal to each other. So therefore, I can theoretically have a state space where I can have infinite number of L orders.
How do you have the pointing vector? Well, you're saying the pointing vector is rotating.
Yes.
Along the direction of propagation as the axis.
Yes.
So initially the pointing vector must be at some angle to the direction of propagation. How is it that possible?
Because how we are generating the light, because there is a fog grating. So when a Gaussian beam comes in, the grating is creating two momentum. And as a resultant, we have, so if we try to calculate the pointing vector of this, so it has one radial component and one azimuthal component, right? So it is not the, so this is actually the phase front which is rotating, right? So it's not on the plane. The electric vector, it's the
Radial means
one along from the center to the, yes, radial is orthogonal to the direction of propagation.
how can you have an orthogonal pointing vector?
Because of this grating, it shifts an amount of light into that. So it's already very well. It was first shown by Allen around 1980.
So you're kind of transferring the energy
Into
from the
the
direction of propagation into the
to a angular momentum. So that's why the light is rotating, right? So these are already experimental, and you can see that. I don't know whether yes. So you can see that these are the lights. So the intensity distribution is annular, right? Because there is no intensity at the center. But as we go on to the higher L order, the ring radius will keep on increasing. And all these modes, they are eigenmodes, so they are orthogonal to each other, right? So we can use this for creating channels in our communication system, right? So our motivation for this study is that if we look into the internet use into the rural and urban area, so we can see that in the worldwide, the internet connectivity to the rural area is very less. And one of the problem is that we cannot have a viable commercial model for which a service provider will put up his infrastructure into a rural area, because the revenue generation will be very low for them. So our objective is that whether we can find a way to give a remote location connectivity using this free space optical communications. So this is that if we look into the scenario of India, nowadays almost all the panchayat office, they have the connection of the Bharat. So we have the optical fiber laid down to the panchayat office, but then we have a remote village where we had no access. So then what we can do is that we can take the signal from the panchayat office and somehow we convert it into a free space optical signal and then you transmit it to the distant village. So for that, we have thought of this architecture, right? So these are the base station RFS transmitter. So they will transmit to a high altitude platform, mostly which is hovering at an altitude of 20 kilometer to 25 kilometer. Then we have considered till now that the connection, the communication link between the base station to the hub will be optical communication. And from the hub to the satellite or another hub, or from the hub to the remote local base station, it can be RSC. The advantage is that if we do for a complete FSO, then we need to have a new class of satellites to be installed there. Our idea is that whether we can introduce in our network architecture which can be compatible with the existing satellite architecture that we have. So therefore, we have taken that from the hub to the next phase, it will be conventional RF or it will be FSO as per demand. But from the ground to the hub, it should be the FSO. Now the problem of this, that this particular architecture puts some kind of restrictions on what we can do. First of all, it's a hovering platform and it's not very high up, it's at the altitude of 20 meters, right? So we cannot put any devices on the hub which are bulky, which have a larger payload, and which can consume a lot of energy. So processing the optical data at the output, rather the processing the image at the output is out of question, because we cannot put adaptive optics there because it will take a lot of power, right? And also it is very hard to maintain the alignment. So we need a kind of correction system where we predict the channel through some probe beam and we figure out the noise into the channel itself, and then we pre-coded the beam with the conjugate of the noise so that the channel itself acts as a corrected system. So here the channel will act as a deformable mirror, and we have, instead of having a pure beam, we are actually uploading a distorted. So this is what is called a pre-correction algorithm. Now there is not much experimental data is available, so we had to devise our simulations to take the data and do the analysis. So this is the basic simulation setup that we have taken. So this is called the split step propagation method using angular scatter. So what we do that we take the chi-in is the input waveform that we can take, and it can be anything. It can be Gaussian, it can be wave mode, a wave beam, it can be lower Gaussian beam, anything. Then it travels for some distance, and then the atmospheric turbulence is represented by a phase screen. What does a phase screen do? So it will not change the intensity, it will introduce local phases into the waveform. So we have some specific mathematical relations that given the meteorological parameter of the environment, how we can create a phase screen so that this phase screen can capture the turbulence effect of the atmosphere itself. So what we do that psi double prime is psi prime multiplied in the phase with this phase screen. Right? Then we again give a free space propagation to the output plane, and it will generate a distorted propagation over some distance. Now, suppose I want to do it for 20 kilometers, right? So I need multiple phase screens to capture the layered structure of the atmosphere, right? Our atmosphere is not uniform. So if we go from the lower end, close to the ground to the high, the density, temperature, pressure, wind speed, everything is changing. So I cannot have a unique phase screen that can represent the atmosphere to the entire land, right? So I need to produce different phase screens according to the meteorological parameter of the different height. Now, for our simulation, we find out that it requires almost 42 phase screens. And then there are a lot of convolution operations there. So it was taking a lot of time. And to do a statistical analysis, you need to produce a huge amount of data. So what we find out that we can actually combine all these phase screens into a single phase screen. And then by placing this single phase screen to a particularly predetermined place, we can generate the same amount of turbulence that we are getting from the extended simulations, right? So I'll just show you the results. So these are the extended medium, the left-hand sides, for the uplink and the downlink scenario. So these are two different things, because in the uplink,
so the position at this first chart, the positions of the phase screen will depend on the atmospheric conditions.
Yes. So once
it's very with time.
Yes, it's also very with time. So the
also we find an equivalent phase screen.
So we can once we have the meteorological data, suppose I have the 42 phase screen. So equivalent phase screen is nothing but sum of these 42 phase screens. Sure. So for one instant I have this. For the next instant I can calculate the 42 phase screens again, and I have the equivalent phase screens. The point is where to put it. We cannot put it at any distance.
So that also depends on the atmospheric conditions.
Yes. So that's why it's a dynamic channel.
What do you do? You just calculate a priori calculation depending on the material data, and then
we take the meteorological data, right? And then we calculate the phase screens for the 20-kilometer channel.
But that itself is going to take time, right?
Yes, but on the other hand, calculating the phase screen is not that much time consuming. Rather, when you have this, so if there are 42 phase screens, you have 42 into 2 convolution operations. And since the beam is propagating,
how much time it takes to get the equivalent phase screen?
The equivalent phase screen, mostly for the 42 phase screens, I can remember, it takes roughly around 1 minute.
But about the time it takes to compute on the distributed system.
Oh, for this entire propagation, if I take out the phase screen calculation part, because that is the same for these two. So it takes around, say, 19 seconds, where this one takes 0.9 seconds, 0.8 seconds. So that's what we have been able to do, right? So here we can show that for the uplink and the downlink scenarios are different, because for the uplink, the beam faces the distortion first because the atmosphere is too much violent near the ground, and then it's mostly dispersive propagation. On the downlink, the dispersive propagation comes first, then through the turbulence. So in case of downlink, the beam distortion is less, where for the uplink, the beam distortion is much larger. But you can see that by the equivalent phase screen method, we can generate the same amount of distortion that we can have. And this is true for any kind of beam, not only Gaussian beam. We also did this for lower Gaussian and Bessel Gaussian. And we can get the equivalent results. So now why we do that? So this is the pre-correction algorithm that we are proposing, is that we have the hovering platform there, and we cannot do some complicated calculations onto that. So what we do is that we send a probe beam from the hub to the ground station. And in the ground station, we do the correction algorithm. So right now we are using what is called the hybrid input-output GS algorithm. So it's an iterative algorithm. So based on the input beam, since we know what the probe we know already, that is Gaussian beam, and from the received intensity, we can calculate what is the phase in the output intensity. And from that, we can actually guess what is the phase distortion is getting introduced. So we might, in the input beam of the signal, we actually multiply the beam in the phase factor with the conjugate of the phase of the distorted phase. And then when the beam is propagating, so it is getting self-corrected through the channel. So these are the few results. So we have taken an OM beam and the input with a L order of +3. Then without pre-correction, the intensity and the phase factor becomes like this. But when we apply the pre-correction, the intensity and the phase comes out this one. Now, what is the advantage of this? That whenever we are trying to do a half communication, there is no question of doing WD, because we cannot put some tunable laser source onto a half platform. So we intend to focus to use only one frequency of light. So instead of doing WTM, we are doing what is called the mode division multiplexity. So we are using different mode to code each channel. So we require only one light source. And generating these OM modes is pretty easy and it's compact. Right? We can simply use a spatial light modulator or a fixed grating, and that can generate it. So this is the results that so far we got. But then there is a problem that running the GS algorithm during a communication process is not very good. So what we are now trying to do is that we are trying to employ what is called a physics-controlled machine learning. So we have taken a synthetic data of 10,000 data of these distorted images and their corresponding phase space. So these are level data. Then we also fit the physics, how we are generating this, right? So both of these goes into the ML algorithm. And from that, ML is trying to calculate. So it's trying to minimize two losses. One is the physics loss and another is the prediction loss. So from this, we are trying to find out whether the ML algorithm, based on the given of the synthetic data, whether it can predict the phase distortion which is getting transmitted to an unknown signal, right? So that work is going on. Now, with this comes hand in hand what is called the quantum key distribution. So this is the famous BB84 protocol. So Alice is one who is trying to send the key to the Bob. So he'll use 4 different bases: horizontal polarization, vertical polarization, and 2 diagonal and anti-diagonal, right? So he will code his bits into this polarization and he will send it to the Bob. Then Bob will do the measurements and will find out if his measurement is coinciding with the Alice. Then he will take that to be true bit. And if it doesn't, then it will discard it. So all the cross, that is where Bob has misinterpreted the same data. So we discard it and the key will be generated through the correct bits, right? What Alice said and Bob actually received in corrected bit. So we can do the same thing with an OM basis, right? So in these cases, there is a problem that when we are using polarization of light, there are only few states available: linear polarization or circular polarization. But whenever we are shifting to orbital angular momentum, then theoretically we have n spaces, right? So we have n variable spaces. So we can have much more complicated encryption key. So I have shown you that we can we have taken just 3 OM nodes, L equal to +1, -1, and 0 order node. And from that, we can create 5 bases, and we send it to that, and Bob will do the measurement, and we can find. So using these 3 only. So what does it take experimentally? So it will take only 1 critic to generate the 3 steps. Because 1 for critic that will generate the +1 and -1 on the 2 first orders, and 0 order sender. So we have this ability into this. So right now we are looking into we are building the experimental setup to test this BB84 protocol. But right now we don't have the single photon source, so we are we have to do with the weak pulse communications. Now this is the third topic that we are also working on right now, and we have a running DST project on that. So this is called the micromotion measurement of the hip implants. So whenever there is a crack or whenever there is an accident, and if the hip joint has to be replaced, so there are metal implants that has to be given into the bone structure. Now, what happens is that you can see the left-hand side, that's a successful implant. On the right-hand side, it's a failure because the prosthetic has gone deeper into the bone structure because of its weight. And as the patient moves, this implant starts to move around, and it can lead to a failure. If the depression is sufficiently high beyond a certain measure, then it's a failure. Now, nowadays, the only technologies that we have, either you have to go for a CT scan or an X-ray. Now, suppose a patient who has gone through this operation, right? It is not possible to take him every now and then to the X-ray machine or CT scan. It's not even body safe. So what we are trying to find out, we are trying to devise a wearable sensor, right? What we can put on the thigh of the patient. And as the patient will move along, the device will pick up how the implant is moving inside the body. And if we can track the motion of this implant, then we can predict also whether this implant is going to hold or it is going to fail. So for this, what we have done, that we have put a Vivaldi antenna, narrowband Vivaldi antenna on the both sides, right? So one is transmitter and there is receiver. And we have picked up that as the implants move, so these are, till now, these are simulative results. But this gives an important insight that as the implant moves inside the body, the frequency, so this is a measurement of S11 parameter, right? So the resonance frequency is shifting. But the frequency shift is of the order of megahertz, and it is very hard to measure with any RF devices. So that's why we come up with this indigenous idea that we take the signal from the microwave sensor, right? And now we use the optical source and we modulate this optical signal with the RF signal that is coming from the sensor, right? So now it's basically amplitude modulation. So what will happen? We have the carrier frequency and we have 2 sidebands. And these sidebands, they carry the information of the RF signal frequency. Now, if we can measure the instantaneous frequency of the sideband, since we know the center frequency of the optical signal, we can find out what is the signal frequency of the RF signal coming in, right? And since the shift of the RF signal can be correlated with the motion of the deep implant, so we are expecting that through this, we will be able to do that. But then our challenge is that it has to be a point of care devices, right? So we cannot have a very big bulky instrument for that. We can have, right now, there are a lot of optical wave meters are there which have kind of femtometer resolutions they can produce, but those are very bulky, right? So we need some devices which can be integrated into the sensor and it can be a wearable solutions.
This frequency is very small.
Very small, mega.
Frequency is
Very small. So it's of the order of, say, micron, few micron. So RF devices, VNA cannot pick up this frequency shift. So this is what is called the optical speckle for frequency measurement. So it's like that if you shine a laser light through a distorted medium, which is static with respect to time. So earlier I have shown you a scattering medium which is dynamic. But now if we have a static which is not changing with time, then if I change the frequency of the wavelength, the scattering pattern will change, right? Now I can create kind of a barcode, right? So I have the static media which is not changing, And I'm shining this medium with different frequency of light and I'm having different speckle patterns. And I know that previously, I calibrated my system. Then when an unknown signal comes in, I'll try to find out with which speckle it has maximum correlation. And from that, I can find out what is the instantaneous frequency. And it can produce a solution which is integrated. So this is a photonic crystal. So entire dimension is not more than 1 meter, right? So what we have done is that this part is photonic waveguides. So these are photonic crystals which can carry light at 1550. And here is the random medium. So these are nothing but air holes dig into the silicon. And they are of the order of say 80 nanometer to 100 nanometer, right? And these are randomly distributed. So it's a static random medium. Now when a light comes in from this port, right? So this is the input port. If the light comes in, it will get scattered and it has 24 ports. So each port will have some amount of energy going into it. So if I placed a detector array on that, so based on the frequency of light which I am, because when I shine light with one frequency, I have one pattern of intensity distribution at the output. Then if I change the frequency, this pattern will change. And now I have an active barcode. So now I can shift my frequency little by little and I can store all the barcodes. Now I put it for unknown signals and I will see that which barcode has the maximum correlation. And I can find out what is the instantaneous frequency of the signal. So here you can see that this is a very preliminary result. This result has already improved. It's an old result. So we can see that the correlation factor is around 0.6, which is at 0.5 nanometer, right? So right now we have achieved which is called 0.01 nanometer, right? So if the frequency shifts by 10 nanometer, then this device will be able to pick up that wavelength shift. So this is one of the. Yes?
10 nanometer is quite big shift.
Not 10 picometer. 10 picometer, 0.01 nanometer, 10 picometer. Right? So I think I misread. So this is the current result that we have, but still we need to go for what is called, so according to the frequency shift, we need to go down to a resolution of femtometer. So that poses some challenge. First of all, we need a light source, which should be frequency stabilized for the femtometer wavelength. Because if the laser source itself, the wavelength is very beyond femtometer, so we cannot measure the frequency shift. Secondly, we have this integrated wavemeter, which can resolve wavelength of the order of 10 to 5 nanometer, femtometer, right? Now, this is the newest one, mostly theoretical. So this is the classical heat engine that we have. So here we have a hot reservoir and then we have a cold reservoir. So the engine is working, it is taking heat from the hot reservoir and it's doing some work and give the rest of the energy to the cold. Now, instead of having this engine, if we replace this with a qubit, then it becomes a quantum heating, right? So now the qubit will interact with either one of the reservoir based on state. Therefore, and we are considering that the output work will be in the form of photon. So that means, suppose we have a two-level atomic system, right? So let me give you this picture, right? So we have a trapped ion inside, and we have a ferrocavity, right? So these are just two mirrors. And these two mirrors, they are coupled to a heat source, right? So they are coupled to a heat bath. Now what happens that if we can create a micrometer, right, which can vibrate, then it will generate a vibrational mode inside, and we can have, and if we shine light into this trapped qubit, right, so we can generate what is called a photon-phonon couple, right? So the mirrors are vibrating at some frequency. So there is a vibrational mode, mechanical vibrational mode inside. And if at any point of time this mechanical vibration is in resonance with the optical mode, so we can have a photon-phonon coupling. And since the mirrors are in connection with the heat bath, then the qubit inside is in way in a connection with the heat bath itself. So now we have two sets of mirror. One is connected to a hot bath, one is connected to a cold bath. And we have written the proper Hamiltonian for it, and we have solved it, and what we have seen is that we have plotted the efficiency with respect to the tuning factor. That means how much the coupling between the photon and phonon is happening. And you can see that the heat engine that we have propose it's not a perfect auto heat engine, it's a quasi auto engine because as you can see that it will keep on losing its energy. It will not oscillate for the entire time, but it can have an efficiency greater than the classical auto cell. So these are very preliminary results. We have just communicated it. So we are planning to do some experiment on this. We are trying to procure the devices. So these are the works, and my head of the department also asked me to use this opportunity. So there is we have the July cycle of the Institute PhD Fellowship is open right now. So the application, the last date is 30th May. So I hope the people who are interested to work in my group, in other groups also, they can come and they can apply through this portal. So with this, I'll end my talk, and if there is any question, I can answer.
Now I'm replaced present the speaker with a payment cover as a token of gratitude.
Thank you.